Today we are solving coin change problem. We are given an integer array coins representing coins of different denominations and an integer amount representing total amount of money we are supposed to make. And we are expected to return the number of combinations that make up the amount. It is important to note that we are expected to return the number of combinations, not the permutations. And they also mentioned we have infinite supply of each kind of coin. Let's try to solve this example. How can we make $5 using coins 1, 2, and 5? One way is to use all ones. The second way is to use 3 ones and 1 2. Third way is 1 1 and 2 2s. The last way is to use just 1 5. You can verify that these are the only 4 ways to make $5. There are no other ways that amount to $5. So how can we come up with an algorithm to do this task? The hint to this question is in the question statement itself, where they expect us to return the total number of combinations. So we have to figure out all the combinations possible that make up the expected amount. Just to save some time, I've already written down all the combinations for the given example. I have represented this problem as a function make that returns number of ways to make $5 using cons 1, 2, and 5. As you can tell, you can divide this problem into these subproblems, where this subproblem indicates number of ways to make $5 using just the coin 1, just the coin 2, just the coin 5, coins 1 and 2, 1, 5, 2, 5, and all 3 coins. As you can see, you can divide these subproblems into more subproblems. For example, number of ways to make $5 is equal to number of ways to make $5 using just the coins 1 because we picked 0 coin 2, plus number of ways to make $3 using just the coin 1 because we picked 1 coin 2, plus number of ways to make $1 using coin 1 because we picked 2 coins 2. Similarly, number of ways to make $5 using all 3 coins is equal to number of ways to make $5 using coins 1 and 2 because we picked 0 coins 5, plus number of ways to make $0 using coins 1 and 2 because we picked 1 coin 5. You may be able to recognize a pattern here. The way to divide a problem into subproblem is by picking 0 coin of final denomination, by picking 1 coin of final denomination, 2 coins of final denomination, so on and so forth. You may be able to also see that some of these subproblems are repeating. For example, this subproblem is same as this subproblem, and this subproblem is same as this subproblem. So this clearly indicates this is a dynamic programming problem, and we should be caching these results of these subproblems so that we can reuse them in the recursive relationship. And based on these subproblems, I have written down this recursive relationship where number of ways to make amount A using coins 1 to coin n is equal to number of ways to make amount A by picking 0 coin Cn and keeping all the other coins from C1 to Cn minus 1, plus number of ways to make A minus Cn amount by picking 1 coin Cn and keeping all the coins from C1 to Cn. We keep using this recursive relationship until we hit the base case where we have to make amount 0 using any number of coins, and there's only one way to make amount 0 is by picking no coins at all. Now let's write the code for this problem. We have been given n different denomination of coins, where n is the length of coins, and we are expected to make amount of money, and we are expected to return number of ways, number of combinations to make that money. So we defined this function make before that returns the number of combinations to make the amount using all the coins. And the way I represent the usage of all the coins is by using the indices here, n-1, where n-1 indicates that we're using all the coins starting from index 0 all the way up to index n-1. So we return this. Next, we have to define the function make, which accepts an amount and the indices up to which we are allowed to use. The first thing to write in any recursive function is the base case, where if the amount we're making is 0, there's only one way to make an amount of 0, by picking no coins. Next we have to write the recursive relationship, which we derived before. I'm going to put that on the bottom left corner of the screen. So number of combinations to make amount A up to index I is number of combinations to make the same amount A without using the coin of the final denomination, plus number of ways to make the amount A minus value of the final denomination. And that's our recursive relationship. In this, we need to make sure we take care of some of the edge conditions, where in this case, where we do not pick the coin of the final denomination, so we get rid of this coin. So eventually we would have gotten rid of all the coins in the list. So that's when I is less than 0, we return 0 because there are no more coins left to pick. And also another edge case is we can only pick a coin if the amount we are supposed to make is greater than or equal to the value of the coin. Otherwise, we return 0. So that's our recursive relationship. Let's try to run this. Let's see again. Oh, okay. Here I missed an argument I. Okay. Let's run this. Now let's submit this. This is most likely going to return a time limit exceeded error. That is because we are not caching the results of the subproblems. There are a lot of overlapping subproblems. Yeah, as you can tell, we got the time limit exceeded error because there are a lot of overlapping subproblems and we are calculating them every single time. So the way to fix this error is to cache the results of overlapping subproblems in a dictionary. So if overlapping subproblems is if we call the function make with the same A and I again and again, those are overlapping subproblems. And if we have already seen those arguments before, we just return the cached result. If not, we save the result and then return it. So this Should fix the error. There we go. This is the top-down approach of solving any dynamic programming problem where we started from the final amount we are supposed to make and then divided it into multiple subproblems and tackle those subproblems individually and then finally combine the results of them. This is the top-down approach. The other way to solve this problem is the bottom-up approach where we solve for the subproblems first and then combine the results of those subproblems. So that is an iterative approach. I usually prefer the top-down approach to solve any dynamic programming problems, but it's good to understand the bottom-up approach as well. Next, let's try to write the code for the bottom-up approach. I'll comment this part out. In the bottom-up approach, we have to iterate through all the possible subproblems. So all the possible values of A and I, and then cache them. So let's define a two-dimensional array to cache these results of subproblems where one of the dimensions is the amount we are trying to make. Amount plus 1 plus 1 is because our arrays are 0 indexed. And the second dimension is the number of coins. So this is the two-dimensional array where we save all the results. Next, we iterate through all the possible values of amount and the coins. Before that, we need to save the base cases first, where the amount we're trying to make is 0 for I in range 1 dp of, for any number of coins left, if we are trying to make the amount 0, there's only one way to make it. So now we iterate through all the possible coins and the amount we are trying to make. I in range 1 to plus 1, and next we're trying to make the amount A in range 1 to the final amount. As you can notice, we're starting from the lower end of the range and then building it up towards the final problem. So let's copy the recursive relationship here. This is the recursive relationship we want. So dp of I and A indicates the number of combinations to make the amount A using I coins is equal to number of combinations of making the same amount A without picking the final coin. That means we have I minus 1 coins left, plus number of ways to make the amount A minus the value of the final coin. I minus 1 because I indicates the number of the coin, and I minus 1 is its indices. So the amount we are trying to make is A minus coins of I minus 1 with all the coins left. So this is the recursive relationship, and we can use the final coin only if the amount we are trying to make is greater than or equal to the value of the final coin, else it will be 0. So this is the recursive relationship, and eventually we return the solution for the final problem, where number of ways to make amount A using all the coins. So this is the final result. Let's try to run this. Passes all the test cases. Submit this. Okay, and as you can see, the submission went through. So, but there's one way to optimize the bottom-up approach. As you can see in this recursive relationship, the current state, which is the number of ways to make amount A using I coins, is only dependent on the previous state, I minus 1. So we do not need the entire two-dimensional array to find the value of the current state. We just need the value of the previous state. So we can use one-dimensional array. We don't need both the dimension. And that dimension is the amount. So let's try to change this array into a one-dimensional array with just the amount. We can get rid of the coins dimension. So the same here, we get rid of the coins dimension. Number of ways to make an amount 0 is there's only one way. Same here, get rid of the coins dimension. Same in the return value as well. Let's try to run this. Passes all the test cases. And the submission went through. If you found this video to be useful, please like the video for the YouTube algorithm. And if you want me to discuss any specific problem, please comment on the video. I'll make sure to post something on that. And I will see you in the next video. Thank you.